Okay, let's get started with our laboratory discussion today. Today we'll be doing a full overview of Chem 100 Experiment 3, Density and Specific Gravity. First and foremost, let's show where to find the lab experiment we'll be working on today. So, Experiment 3, Density and Specific Gravity, is assigned as part of the second set of laboratory experiments that we'll be working through. There is a lab page for this lab activity, and that's where we'll be collecting all of the data that we're going to be using to complete our lab report. There is also a pre-lab lecture recording. So if you need additional background on the theory behind this lab, I would encourage you to reference the pre-lab lecture recording video. Let's open up the lab page now. So this is what the lab page looks like for experiment 3, density and specific gravity. And let's open up the lab experiment in the lab manual. So this is the starting page for experiment 3, density and specific gravity. Again, as always, there's some introductory information. So you can read over that to get a little bit of insight into the background behind today's experiment. And then there's the experimental procedure, which again, we'll be going through momentarily. And finally, if you scroll all the way down, you'll see the pre-lab study questions, which we'll be skipping, and the report sheet. So we're going to be filling in this Lab 3 report sheet using the data found on the Experiment 3 page. And we'll be turning everything into the lab submission page once we've completed this lab experiment and filled in all of the report sheets. So let's take a look at the experiment 3 lab page. Again, there's an introduction section, which you can read over on your own time. And let's move on now to the experimental procedure. Let's start going through the procedure and let's start processing the data found on this lab page and inputting that data onto our report sheet. So I've already taken the liberty of transporting the report sheet onto my virtual lab notebook, and let's work through each part of this laboratory together. So first and foremost, let's look over part A and let's read the procedure. So going to the experiment procedure for part A, we're going to place about 20 milliliters of water into a 50 ml graduated cylinder. We're going to record the volume and we're going to weigh a beaker, record its mass. We're going to pour the water into the beaker and weigh the beaker and record the combined mass. We'll then calculate the mass of the water via difference, and then we'll calculate the density of the water by dividing mass and volume. Now, this procedure is fine, but there's an even faster way to do this. We don't need to necessarily weigh a beaker. We can just take an empty graduated cylinder, pour the water in, and weigh the graduated cylinder to get the mass of water. So let's take a look at the data and let's show how we're going to process the data provided on the lab page. Okay, so here we have our empty graduated cylinder. The mass is found here. So let's just write down that mass on our report sheet. Okay, so for the density of water, so instead of the mass of the beaker, let's just look at the mass of the graduated cylinder. So in this case, if we look at the lab page, we have a mass of 72.1 grams. Okay, perfect. Now, let's scroll down. And now we have the mass of the graduated cylinder and water, which we read out as 93.2 grams. So let's transfer that. This already looks pretty good considering the density of water is around 1 gram per milliliter. If we add about 20 milliliters of water, we'd expect the mass to go up by about 20 grams. Okay, now for the mass of liquid, all we have to do is subtract the mass of the empty graduated cylinder from the mass of the graduated cylinder plus the liquid, in this case, water. So subtracting these two values, that gives us 21.1 grams. So the mass of the liquid in this case would be 21.1 grams. And then we have that data inputted. Now let's take a volume reading. So the volume of water in the graduated cylinder, again, we're going to read from the bottom of the meniscus at eye level. Let's draw that in. So just as a check, to go 10 milliliters, it takes us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It takes us 10 tick marks. Thus, 1 tick mark, each of those little graduated marks, corresponds to a milliliter. And we know that 1/10 of a tick corresponds to 1/10 of a milliliter, which is 0.1 milliliters. You always have to go through this step before you take a measurement on a graduated device, because you need to figure out what each of these graduated marks are actually representing in terms of mass, volume, etc. So in this case, we're pretty close to the second mark. So I'd read this as 21.8 milliliters, 22.0, anything in that range would also be acceptable. So now that I have my volume reading for the volume of water in this graduated cylinder, I'm just going to transfer that data into my lab notebook. Let me just make sure I record this, 21.8, okay. Wonderful. So we have the volume, we have the mass of liquid. So if density corresponds to mass over volume, we have a mass of 21.1 grams over a volume of 21.8 milliliters. Both of these inputs have 3 significant figures, so our final answer should have 3 significant figures. So let's calculate this now. So we have 21.1 divided by 21.8, and that in turn gives us a density of 0.9678. You can add additional numbers, but we only need the 4th digit because we're going to round this to 3 significant digits. 8 is clearly greater than or equal to 5, so we round up to 0.968 grams per milliliter, which is reasonably close to the actual density of water at room temperature, which is closer to 0.98, 0.99 gram per mil. Okay, so we've determined the density of water. We're going to use the exact same procedure to figure out the density of an unknown liquid. Again, as always, instead of using a beaker, we're going to use a graduated cylinder. It also, the reason why we're using a graduated cylinder is we avoid an issue if we lose liquid during transfer, we get a less accurate density reading. So just putting the liquid directly in the graduated cylinder and weighing the graduated cylinder ensures all of the liquid that we weigh is actually liquid found in the graduated cylinder. So let's take a look at part A2 and let's read the procedure. So again, we're doing the exact same procedure, except this time we're substituting water with an unknown liquid. In this case, the unknown liquid is a solution of isopropyl alcohol. Okay, so again, as always, we have the mass of the empty graduated cylinder. And this is a sign that we're exercising reasonably good lab technique, is that the mass of the empty graduated cylinder is pretty consistent across our two trials. So let's just write that down. So the mass of the empty graduated cylinder, 72 point, let me just check one more time, 0.0 grams. Okay, now let's scroll down and let's look at the mass of the unknown liquid and the graduated cylinder. That is 89.2 grams. So let's record that. Okay, now let's look at the mass of liquid. That's a calculation. So to obtain the mass of the liquid sample, we take the mass of the beaker plus liquid minus the mass of the empty beaker. Or in this case, we take the mass of the graduated cylinder in liquid and we subtract the mass of the empty graduated cylinder. So in this case, we take 89.2 minus 72.0, and that in turn gives us 17.2 grams. Okay, now we have to take a volume reading. So let's scroll down and let's look at the volume of the unknown liquid. So in this case, as always, we're dealing with the same graduated cylinder as before. So we know 1 tick mark corresponds to a mil, and we know 1/10 of a tick is 0.1 milliliters. This is exactly the same graduated cylinder that we've used previously. The graduated marks are the same, and the estimated digit is going to be pretty much the same magnitude in the tenths place. Okay, so we see that we're somewhere between 20 and 21. 20.6 milliliters would be a reasonable estimate. And of course, your measured values may be slightly different. Okay, so let's now transfer this. So we have a volume of 20.6 milliliters. To calculate density, we have to take the mass over volume. So we have 17.2 grams over 20.6 milliliters. So let's enter this now into our calculator. 17.2 over 20.6, and that gives us 0.8349. And we don't have to include additional digits because, again, these two initial measurements have 3 sig figs, so our final answer needs to be rounded to 3 significant figures. As a result, we look 1 space to the right, 9 is greater than or equal to 5, and thus we round up. That gives us 0.835 gram per milliliter. As you notice, the unknown liquid has a substantially lower density than that of water. Wonderful. So we've completed parts A1 and A2. Let's look at part B, which concerns specific gravity. So in this case, we have some instructions, some special instructions, and an alternative procedure. We are not doing the hydrometer measurements for part B in this case. And instead, we're calculating the specific gravity by dividing the density by the literature density of water. Specific gravity is unitless and can be viewed as a standardized density relative to the density of that of water. So let's calculate that. So for the specific gravity of water, all we have to do is take our input value of 0.968 grams per milliliter, and we're going to divide it by the density of water, which is 1.00 grams per mil. That gives us a specific gravity value that we've determined from our prior measurements as 0.968. Specific gravity is unitless. The specific gravity of the liquid sample, of course, can be obtained by the same method. We take the density that we measured and we divide by the density of pure water, which is 1.00 gram per mil, roughly. That in turn gives us 0.835 as the specific gravity of our liquid sample. We are skipping the hydrometer measurements for this portion of the laboratory. So, key things: specific gravity is unitless, and specific gravity is derived from the density of a given solution, liquid that you've measured. Okay, now let's move on to part C, where we look at the density of solids. So again, let's read through our procedure. So for the density of solids, we're going to obtain a metal object. We're going to weigh and record the mass. We're going to obtain a graduated cylinder. We're going to add water to the graduated cylinder and record the volume of water. From there, we're going to add the object into the water and record the final water level in milliliters. From there, we can calculate the volume of the object via water displacement. And then, given that we know the mass and volume, we're going to calculate the density. From there, we're going to compare the density to the density table found in your lab manual, and you can in turn assign the identity of the solid. So, let's go through this part of the lab together now. In this case, I provided you a table in addition to the lab manual table that you can use to reference, which contains the density of many common metals and non-metal materials. Okay, so first and foremost, we have an empty beaker. Let's record the mass of that empty beaker. Again, we're determining the mass of the solid via difference. So we need the mass of the empty beaker here. So we have 31.0 grams. We need to know the mass of the beaker plus the solid. So let's see if we have that data. So the mass of the beaker plus the solid sample would be 51.1 grams. So then the mass of the solid can be obtained by taking the difference between these two values. So 51.1 grams minus 31.0 grams. That in turn gives us, we have 20.1 grams of solid. Okay, now let's look and find our graduated cylinder, which contains some water. So in this case, the volume of water before solid addition, we're 1, 2, 3, 4, 5. We're a little bit past 35. So I'd say 35.1 milliliters would be a reasonable approximation and a reasonable measurement in this case. So let's transfer this reading now. So the initial water level would be 35.1 milliliters. Okay, now we add the solid into the graduated cylinder and the water level, of course, will rise equal to the volume of the solid that we've added. As you can see, the solid's at the bottom and the water level has increased. Let's take our final volume reading. So we're 35, 36, 37, 38. We're not quite at 38 yet, so 37.8 milliliters. That would be more than fine. Okay, there's also another photo that has a different perspective. And also we can see very clearly we're not quite at 38. 37.8 would be a reasonable reading in this case. Okay, so let's transfer this volume reading. So the final water level with solid was 37.8 milliliters. So the volume of the solid can be obtained by taking the final volume minus the initial volume. And in turn, that gives us 37.8 milliliters minus 35.1 milliliters, which in turn gives us 2.7 milliliters as our volume of the solid. So if density corresponds to mass over volume, we have 20.1 grams divided by 2.7 milliliters. Let's input this into our calculator, 20.1 over 2.7. That in turn gives us 7.444 gram per milliliter. But because this bottom input only has two significant figures, we're going to need to round our final answer to two significant figures. Because 4 is less than 5, we round down, and that gives us 7.4 gram per milliliter. From here now, we can go to our density table, and let's use the density table in the lab manual. And we see that it doesn't quite match any of the metals, but 7.4 grams per mil, that density is closest to that of tin. In reality, for those curious, the actual metal composition of a penny, it's mostly zinc with just a copper coating on the outside. Again, our density measurement is reasonably accurate. However, if we were to use a more precise balance and a more precise graduated cylinder, we'd be able to report more significant digits, and maybe our calculated value would in turn be a little bit more precise, and in turn, we may see less of these rounding errors that we're seeing now. Okay, so we've measured the density of our solid sample. So let's now talk about determining density via a graphing method. So let's take a look at part D. Again, there are a lot of pieces of data that we have to collect. So let's walk through that. So first, let's read the procedure. So in this case, we're going to measure the volume and mass of 5 different samples of the same metal, and we're going to use that to prepare a graph. So we're going to start by placing a volume of water in a graduated cylinder. We're going to record that volume. We're going to weigh the cylinder and water on a balance and record the mass. We'll then add a few pieces of our metal sample. Then we'll record the total mass and the new volume found in the graduated cylinder. We're then going to repeat this process of adding metal pieces, recording the new mass, and recording the new volume. We'll do this for in total the addition of 5 separate batches of metal pieces. Okay, so let's now take a look at the lab page and let's start collecting some data. So we have the initial mass of the graduated cylinder and water. So we have an initial mass. Let's make sure we're reading this correctly, of 190.8. grams. The type of metal, we're going to be looking at a series of quarters. And by the end of this lab, we're going to be able to estimate what is the metal composition of a quarter via density. Looking at the initial volume of water, let's look at the initial volume of water photo. We see that in this case, let's get out the drawing tool. We're dealing with the same graduated cylinder as before. We're at the 1, 2, 3. We're close to the 54 mark, not quite at 55. So 54.5 milliliters would be a reasonable reading in this case. So let's transfer that reading now to our report sheet. So we have initial volume of 54.5 milliliters. Okay, now we're going to start adding metal pieces. And the total mass of the graduated cylinder, water, and metal pieces are going to be recorded. And then we'll also record the total volume of the water and the metal pieces. So let's start taking those readings. So we have the cylinder, water, and the first set of metal pieces, and we have a mass of 202.2 grams. Okay. From here now, we're going to need to record the total volume. So again, in this case, we are somewhere past 55. It looks like we're pretty much right on the mark for 56. So we can write this as 56.0 milliliters. So let's transfer this reading onto our notebook. Okay, so we finished recording the total mass and volume for the first solid addition. Let's repeat this process. So now we're dealing with the second solid addition. And in this case, we have a total mass of 213.5 grams. So let's write that down. Now, one quick way to make sure you're recording the data properly is that if we are adding the same amount of the same solid, the density should be the same. And so the mass and volume should increase in about the same increment. If you're noticing that the mass is massively increasing or the volume is massively increasing, or if it's not increasing substantially compared to your previous trials, likely there was an error made in how you recorded the mass or volume. So always just check. If we're determining the density of the sample graphically, you should expect a consistent, steady increase in mass and volume as you continue adding additional aliquots, additional portions of the same solid. Okay, so we recorded the mass. Now let's record the volume. So this is the total volume after the second portion of solid was added. So in this case, as you can see, we're now past 56. We're pretty much right on the mark for 57 mils. So I'm going to record this as 57.0 milliliters. Okay, so let's transfer that data onto our report sheet. Okay, now let's continue on to the third solid addition. So in this case, we have the total mass, which in this case is 224.8 grams. Okay, now let's record the volume. So in this case, we're 56, 57, 58, 59. It looks like we're at about 58.6 milliliters, give or take. Somewhere between 58 and 59 milliliters. So let's record that volume. Okay, now let's continue on to our last and final solid addition. So in this case, we have a total mass of 236.1 grams. Now let's move on and record the volume. So in this case, we are pretty much right on the line for 60 milliliters. So I'd record this as 60.0 milliliters. Perfect. So let's transfer that data onto our report sheet. Okay, so we've completely filled in our data table. Now we're ready to do some calculations. For those curious, I added an additional trial just to show that this trend maintains consistent, even as we continue to add solid. From here, let's get started with the calculations now. And in this case, we're asked to calculate the mass of the metal pieces via difference. We're going to calculate the volume of the metal pieces via difference, and then we'll calculate the density for the metal in each trial. We're then going to draw a graph where we graph mass on the y-axis and volume on the x-axis, and we'll work through that together. Okay, so first let's complete the calculations. So for the mass of the metal pieces, we have to determine that via difference. So we take the mass of the graduated cylinder, water, and metal pieces. So in this case, we're going to calculate that for our first trial here. So we have 202.2 grams. And then we're going to subtract out the mass of the graduated cylinder and water, which is 190.8 grams. Again, via subtraction, we retain one decimal place in this case. So we have 202.2 minus 190.8. And that in turn gives us 11.4 grams. To determine the volume of the metal pieces, we're going to determine that via difference. So we're going to take the volume of the water and metal pieces from this first solid addition trial and subtract out the initial volume of water. That in turn gives us a final value of 1.5 milliliters. And if density is defined as mass over volume, to calculate the density, we take the mass of 11.4 over the volume of 1.5 milliliters. So we have 11.4 grams over 1.5 milliliters. Because one of our inputs only has 2 sig figs, the final answer will only have 2 sig figs. So we get out, interestingly enough, a final density of 7.6 gram per milliliter, which is already rounded. Sometimes that happens. Okay, let's continue on the calculations. So to calculate the mass of metal pieces in our second solid addition, again, we take the total mass and we subtract out the mass of the graduated cylinder and water. Entering this into our calculator, that gives us a mass of 22.7 grams. Calculating the volume, we take our total volume and we subtract out the volume of the graduated cylinder and the water, only in the graduated cylinder. So anytime the water level increases, that's due to the volume of the solid that we've added. That in turn gives us 2.5 milliliters. To calculate the density, we take the mass, which is 22.7 grams, over the volume, which is 2.5 milliliters. Punching this into our calculator, that gives us a density of 9.08, which we round up to 9.1 gram per milliliter. So we are seeing a bit of variability. That is not a huge deal. Okay, let's continue on with these calculations. Again, we're determining the mass via difference. So let's continue on with these calculations. Let's move this calculator a little bit further. We'll move this around just so that way it's not blocking anything important. So we have 224.8 minus 190.8, and that gives us a mass of 34.0 grams. For the volume, we have 58.6 milliliters minus 54.5 milliliters. And that in turn gives us a volume of 4.1 milliliters. Now for the density, we take our mass, which is 34.0 grams, over the volume, which is 4.1 milliliters. I'm just writing it this way for space considerations. So we have 34.0 divided by 4.1, and that gives us a density of 8.29 gram per mil that we round to 8.3 gram per milliliter. Okay, one more calculation to do and then we're done. We have 236.1 grams minus 190.8 grams. So we're determining the total mass of metal pieces. We have 236.1 minus 190.8, and that in turn gives us 45.3 grams. To calculate the volume, we have 60.0 milliliters. We subtract out the volume of water, and that in turn gives us the volume of the metal pieces. So we have 60.0 minus 54.5, and that gives us a volume of 5.5 milliliters. From here, if the density is just the mass over volume, we have 45.3 grams over 5.5 milliliters. Let's punch this into our calculator now. And that in turn gives us 8.236 gram per milliliter that we round to two significant digits, which we've written as 8.2 gram per milliliter. Okay, so we've completed the calculations in terms of the mass of metal pieces, volume of metal pieces, and density. And we're going to use the mass of metal pieces and volume of metal pieces to prepare our graph. Now, it's important we talk a little bit about rational graph design. You want to make sure that your X and Y axis on your graph are encompassing all of the data values you'll want to include. So we see, for example, the volume goes from about 1 all the way to 6 milliliters. And we see here that if we want to include and we want to make sure our graph is as large as possible in the space allotted, we're going to try to divide up all of these squares that we have into reasonable chunks to cover these 6 milliliters. So in this case, We have 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. 2. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. 1, 2, 3, 4, 5. So if we split up each of these little squares as counting about 0.2 milliliters, then we can cover the full 6 milliliters in the entire length of our graph. Now, in terms of the mass ranges from about 11 all the way to 45. And given that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, about 20. Well, if I want to go all the way up to 45 and I have marks of 20, let's put 50 as the upper bound because that's encompasses 45. And if we divide by 20, we see that each of these little marks are going to be worth about 2.5. So 5, 10, 15, 20, 25. These are all in grams, of course. 30, 35, 40, 45, 50. Reasonable enough. So when we plot our data points, they're going to be somewhere in this graph, and the plotted data will encompass at least 75% of the graph. You want to make sure that your plotted line isn't too small. Otherwise, it's really hard to draw a reasonable fit. It's really difficult to do any extrapolation or interpolation. And if we have the space, you might as well use it to make it much easier to plot the data points. Okay, so let's now start adding our data points now. So the first data point, we have a mass of about 11.5 and a volume of 1.5. So the volume is about here. The mass is somewhere around here. Okay, so we have our first data point added. Okay, our second data point has a mass of about 22 and a volume of 2.5. About here. The third case, the third data point, we have a mass of about 34 and a volume about 4.1. So 34 is about here. 4.1 about here. Okay, perfect. And our final data point, we have a mass about 45 and a volume about 5.5. About right here. Okay, now what we're going to do is we're going to draw a single best fit line. Do that, we break out a ruler, and we're not trying to get every single point. We're trying to make sure that the best fit line crosses as many points as possible, as closely as possible. Okay. Additionally, because the density is always going to be the density line should cross through 0, 0, ideally, if you can set it up that way. So we're going to get out a ruler. And let's move this down a little bit. Okay, and now let's draw the best fit line. Okay, perfect. Let's put away the ruler. So now we have a best fit line encompassing our data points. And now what we can do is we can pick any 2 points on this line and we can use it to calculate the density. So I'm going to arbitrarily pick the points that are farthest out. I'm going to pick this data point and this data point right here. And we can use it to calculate the density. So in this case, we're going to take our second mass, which is 45.3 grams, minus the first mass, which is 11.4 grams. And we're going to divide by the second volume, which is 5.5 milliliters, minus the first volume, which is 1.5 milliliters. So I chose these 2 data points arbitrarily. You can pick any 2 points on the line to calculate the slope. And the slope corresponds to the density. The slope is the rise over run, the mass over volume. I like to choose points that correspond to the data points that I have collected. In this case, just because these 2 points represent the start and end of the line. Okay, so let's compute out the mass difference and the volume difference. So we have 45.3 minus 11.4. That gives us 33.9 grams divided by 5.5 minus 1.5, which is 4.0 milliliters. Remember, we retain 1 decimal place during subtraction because the least number of decimal places between these 2 numbers is 1 decimal place. We now divide these 2 values, and as we can see, the bottom number has 2 significant figures, and as such, our final answer needs to be rounded to 2 significant figures. So we take 33.9 divided by 4.0, that gives us 8.475 gram per mil, which we round, and that in turn will give us a rounded, oops, one moment. That in turn will give us a rounded value of 8.5 grams per milliliter. Wonderful. So we've completed the graphing portion of this lab. We've generated a graph. We've generated a best fit line. We've used the best fit line to calculate the density of the metal graphically, and we've reported the density of the metal graphically. So with that, the only thing remaining now are the post-lab questions, which you will answer in its entirety. To ensure that everyone has the opportunity for additional practice, you'll be completing the post-lab questions individually. Make sure to complete all of the post-lab questions, ensure that all of your report sheets are fully complete, and then make sure to submit your completed laboratory report sheets on Canvas. This concludes our full walkthrough of Chem 100 Experiment 3, Density and Specific Gravity, and you'll be seeing these example report sheets uploaded and available on Canvas alongside this laboratory run-through recording.